Hello everyone. Okay, welcome back to more of making a single board computer with a 6502 based CPU. So I think I said around the end of the last video that the worst thing that could happen to me now is that I have a misprogrammed ROM. So here's my EEP ROM, and I said probably the worst thing that could happen to me is that I had programmed this thing incorrectly, that maybe one of the bytes was wrong, and so the program was not correct, and that's why it wasn't running right. I was wrong. That was actually far from the worst thing that could happen to me. I had a few different problems trying to get this to work properly, and I'm still not sure exactly why it wasn't working. I have a theory, and I think I know why it didn't work, but I'll try to explain what was going on. I thought I had a timing problem because remember in the first video when we ran the CPU, it looked like the CPU was running. I mean, it was going through. It looked like it was going through the different memory addresses. It looked like it was doing the right thing. But when I tried to get it to run a program from the ROM chip, the CPU would just completely freak out. It just wouldn't run the right instructions at all. And so I thought that probably what was happening was it wasn't reading the ROM properly. And my first suspicion was a timing problem because, you know, it's pretty straightforward. I mean, a CPU sends an address to the memory chip through the address bus, and then it gets a byte back. It gets a byte out of the ROM chip back. That's really all that needs to happen. And if it can't do that much, then the only thing I could really think of at the time was it must be a timing problem. Maybe there's some, you know, the thing is, when all this stuff happens at high speed, when you're running these things at 1 megahertz, I mean, 1 megahertz is not even that fast by today's standards because, today's computers have CPUs that run at a few gigahertz, which is, like on the order of around 1,000 times as fast. But, a megahertz is still 1 million times a second. A megahertz cycle is still fast enough that things can go wrong if you have some timing issues. So I thought that, okay, maybe I had some timing problems, and a timing problem is probably the worst kind of problem that you can have when building a computer like this. A lot of computers fail because of some nanosecond level glitch that happens, just for like a tiny fraction of a second, like a billionth of a second, there is some signal that comes too late or too soon, and that completely screws up the timing of the whole system. So it's not unheard of for that kind of thing to take months and months to diagnose and work out and figure out how to ameliorate such a problem. So I thought, oh boy, I've really done it now. I've got myself into a situation where I might not be able to diagnose or solve this problem without some really expensive test equipment. I thought about getting a logic analyzer, because really what you'd need to analyze something like that is a logic analyzer. Not even an oscilloscope, because an oscilloscope just checks usually one signal at a time. A logic analyzer is basically an oscilloscope with several leads. So like if you imagine an oscilloscope with something like, I don't know, maybe something like 32 inputs, because you need to monitor all the inputs on all these things at the same time. So you need to monitor the 16 lines of the address bus and the 8 lines of the data bus all at once. That's basically a logic analyzer. And, a real professional quality logic analyzer for something like this, if you're really doing something for real, can easily cost $20,000 to $40,000, which I obviously wasn't going to invest just for a project like this. They do make smaller logic analyzers for sort of home and hobbyist users. You can get those for, I think you can find something like that on Amazon for probably less than $100, which is, it's affordable, but it wasn't really something that I was willing to invest in for something like this because, again, this project, I'm not planning on doing anything with this when it's done. This is really just something for these YouTube videos, and then when it's done, I'm probably not going to use it for anything practical after that, or even impractical. So it's really just for these videos. So I didn't want to spend a whole lot of money on getting something to work that was just, just for a couple of demonstration YouTube videos. So I thought about getting a logic analyzer, but I didn't want to do that. And, it's really difficult because, Usually, when you have a system, when you have a working system, it's a lot easier to diagnose things because there's usually one part that's not working. And so, if you already have a working system, then you can start changing things one at a time. So, if you change one part, like if I change this part and then it stops working, I can assume, okay, there's a problem with this part. Something here is not working right. But the setup that I had was really so simple. All I really had was the CPU and the ROM chip. They both seemed to work individually. I hand checked the ROM and I checked, if you put the right wires on the ROM chip and check what values come out, it was giving the right values, so that seemed to work. So either the CPU was completely wrong, there was just something totally wrong that the CPU was doing, or the ROM chip was not fast enough. Somehow it wasn't keeping up with the CPU, which I found very unlikely because this is a pretty new ROM chip. It's not like, the CPU is based on technology from 40 years ago, and this ROM chip is designed for today's design, so I found it extremely likely that the ROM chip was too slow. I thought maybe this housing, like this big housing for the SOIC chip, maybe this was creating some kind of delay because the physical effects of being in a huge housing like this obviously adds some impedance to the wires, and maybe that was creating enough, I think the correct term is inductive reactance, that it was slowing down the signals enough or impeding the signals somehow. So, I thought about stuff like that. And again, those kinds of problems are really tough because, what we've been doing so far is actually very simple. I realize it might not seem simple to some people. For some people, it might just seem like, this is completely crazy. Like, what is he doing? But honestly, this is really not much more than just. This doesn't sound too condescending, but this is almost really just like connect the dots. Because, if you look back at this is the diagram of the CPU. So really all that I did here with these wires is I just connected the wires with the names here on the CPU to the wires with the same name on the ROM chip. So connect A0 on the CPU to A0 on the ROM chip, connect A1 to A1, A2 to A2, and so on. So it really is almost just like playing connect the dots. Just run wires from this point to that point. It may look complicated, but it's really not that complex, honestly. It's designed to be simple enough that hobbyists doing it at home don't need a PhD in electrical engineering to get it to work. But really, I thought that, okay, if I'm in a situation now where I really have a fundamental timing problem, that's just it's just not going to that I can't diagnose without spending thousands of dollars on diagnostic equipment, then I might just give up and just not finish the project. But as kind of a last resort, what I did. I took advantage of something nice that you can do with this version of the 6502. So you couldn't do this with the original 6502, but what I did with this chip is I decided to slow it down. One of the really nice things about the Western Digital, the WDC version of the 6502, the 65C02, for hobbyists is you can slow the clock way down. So I made a clock cycle or a clock circuit. Remember in the first video I made a clock circuit that runs at 1 megahertz. But you can slow the clock down on this thing all the way to 0. You could not do that with the original 6502. On the original 6502, if you brought that clock down to just a stop, if you just stopped it entirely, the CPU would crash instantly because it was built inside with what are called dynamic registers. It's kind of like how DRAM works. So if you know how DRAM versus SRAM works, SRAM is stable. DRAM has the problem that it needs to be continually refreshed multiple times a second because the value, the bit that's stored in a DRAM cell, in a DRAM memory chip, is kept alive by a tiny capacitor, but that capacitor only holds enough charge to power that bit for a fraction of a second. So in your computer, many times a second, the RAM has to be continually refreshed and refreshed and refreshed, or else the computer will crash right away. The original 6502 did the same thing with its internal registers. The registers were also they weren't proper stable registers. They were actually based on a capacitor that was powered up for for one CPU cycle, and then in the next cycle that capacitor would be refreshed and recharged. So if you stopped the clock so that those registers in the CPU stopped getting updated, that was it. The CPU would crash instantly, and there would be no recovery other than to just reset the CPU and start over. Basically, a reboot of the computer. So you couldn't do that with the original C502, but you can do that with this. This chip is the WDC 165 CO2 is so designed that you can slow the clock way, way down. You can even hand clock it. So you can stop it, and what some people like to do is, have a little button like this, and you can hand clock it. So basically, whenever you push the button, that's one clock cycle. So you can you can single step through a program by just pressing the button over and over, and that will advance the CPU by one clock cycle each time. Kind of cool. That's actually very cool for when you want to diagnose something. If you have something really weird going on and you want to step through the program one instruction at a time. But I didn't really want to do that. I didn't want to have to keep pressing a button. So what I did is I got a 4093. And this is a diagram of that chip. And it's a very simple chip. It's really just 4 NAND gates, 4 not AND gates. But we don't use, I'm not using this for the NAND gate functionality. In fact, I'm just going to use one of these gates. I'm going to join the two inputs together. Really, the reason why I'm using this is because this chip uses Schmidt trigger outputs. And that's kind of useful for an application like this. What is a Schmidt trigger? Basically, what that means is instead of, let me try to explain it a bit. So basically the way that that any information inside a computer is stored is as some kind of electrical voltage. So if I say, basically there's just some point, some voltage where if the voltage is above that level, then the computer says, okay, that's a 1, that's a binary 1. And if it's below that voltage, then the computer says that's a binary 0. So, high or low, 1 or 0, that's it. That's really all it understands. The whole computer just works by checking voltages and just comparing voltages and seeing is this voltage higher than what I think is the threshold for a 1, or is it lower than what I think the threshold is. The problem that you can have, the problem that sometimes happens is, technically what's supposed to happen is digital signals are supposed to be so-called square waves, which means they just go up like that, they go straight up, and then sometime later they go straight down. So they're not supposed to, angle like that. But in real life, we live in a real world with real laws of physics and science. And so in reality, the line never goes straight up. You can't just instantly go from 0 volts to some other number of volts. There is some finite time delay. There's some length of time. And maybe it's just a tiny, tiny fraction of a second, but there's some amount of time that it takes to go from here to here. So in practice, all electrical signals in the real world are kind of slanted like this. And what can happen then is if it doesn't go up fast enough, if it doesn't go up abruptly or sharply enough, what can happen is you get this weird sort of kind of oscillation, because when the signal's around here and when it's hanging around here and not when it's right at that threshold and it's not moving fast enough, the CPU can kind of wobble back and forth. They can say, okay, it's a 1, up, no, it's a 0, up, 1, up, 1, 0, up, and it'll just keep kind of going back and forth like that. What a Schmidt trigger does, instead of just having one line like this, and it says, okay, above the line is a 1, below the line is a 0, it actually has 2 thresholds. And it does not activate, it does not turn on until you're above this threshold. So if you have a signal that goes in like this, it turns on here. It turns on at that point, but when the signal goes back down, it doesn't turn off when the signal passes this point. It doesn't turn off until the signal passes the lower threshold. So basically what happens is you've got a transition here and a transition here. Going up through the upper threshold, which will turn it on, and going down through the lower threshold will turn it off. But it doesn't, it won't oscillate around one point the way a single threshold can sometimes do. That's what this symbol here means. This symbol here is the symbol for what's called hysteresis, not to be confused with hysteria. And hysteresis basically means that the condition of something depends on its history. So it's not just like this is 1, this is 0. It's more like, okay, how did we get to this point? Did it come down from somewhere? Like, did it, did it come down from was it a 1 when it reached this area, or was it a 0? If you get to this point and the signal is a 0, then it becomes a 1. But if the signal was already a 1 when you hit this point, it doesn't go down to 0. That's kind of what hysteresis means in this context. So there are different chips that use Schmidt triggers, but the 4093 happens to be a relatively cheap and available one. I think this chip cost me 50 cents. Like, I'm not even exaggerating. It literally cost like 50 cents. I think that was what I paid for this. It's a cheap and relatively readily available chip that gives you a Schmidt trigger. There are other chips that also give you Schmidt triggers, but this is one of the most common and cheapest and simplest, so it's good to use. But the clock circuit that I'm using, so what you see here, this clock circuit that I have up here, this is not the clock circuit from the first video that I made with that 7404 inverter chip and the crystal oscillator and so on. This is a very different and much simpler circuit, actually. The way that this circuit looks is, what did I do? What did I do? I think I connected, right, I actually shorted pins 1 and 2 to each other. So I actually shorted the two inputs of that NAND gate together so that instead of being a NAND gate, it basically just works like an inverter. It's just an inverter. So when a 1 goes in here, the output is 0, and then when a 0 goes in here, the output is 1. That's it. So it's basically it's an inverter with a Schmidt trigger. So these two are shorted together, and then I believe what I did is, and then I connected these to ground through a capacitor. So this here is a little, it's actually, I don't know if you can see it very well on the camera. It's this little black thing there is a, see that little black thing there? That is a little electrolytic capacitor. I believe it's 10 microfarads, if I'm not mistaken. And that just acts as a container of electricity, basically. And then, and then there's just a resistor, which, so there's a resistor here, which connects that area to the output of the gate. You can tell I'm American because I draw a resistor with a zigzag line like this. Europeans draw resistors just as a rectangle like that, but I draw a resistor like that, and so it's kind of an American thing. But anyway, okay, so really what we have here is just a very simple example of a relaxation oscillator. So what happens is this capacitor will charge up, but once it's charged up and the Schmidt trigger triggers, it will, so basically what happens is when the Schmidt trigger is on, it charges up this capacitor because this is positive and this is ground, so the capacitor will slowly charge up until the voltage here reaches a positive enough point that shuts off. Then the capacitor will drain out through that resistor into this now negative or into this now 0 region here. So the capacitor will drain out through the resistor. So it creates an oscillation, but it's a nice stable oscillation because of the Schmidt trigger. So again, it won't wobble, it won't like kind of ring or oscillate around a certain point. It will click on and off at certain set points. So you get a relatively stable square wave with this, and you can control the speed of that square wave by changing the values of these components. So the bigger the capacitor, basically the more capacitance the capacitor has, the slower the cycle will be because the longer it takes for the capacitor to drain out and fill up. And the same with the resistor. The larger the resistor, the longer it will take for that capacitor to drain out. And so a larger capacitor or a higher valued capacitor or a higher valued resistor will give you a slower cycle. And then if you want to go faster, you can use a lower valued resistor or a lower valued capacitor. So this is a very simple circuit, but it works. It works in creating a square wave with nice clean transitions, which obviously you need for a CPU like this. And I tried using that with this CPU. Again, that's a nice thing that that you get with this version of the 6502. You can run it nice and slow. You can run it really slow if you want to, so you can watch the logic. If you want, you can probe different pins and see what all the different bus pins are doing and kind of get an idea of what's going on. And that's a luxury that you wouldn't have with the original 6502. So I took advantage of that luxury and tried to diagnose what was going on here. And it seemed like things were a little better, but the CPU would still crash. It would still just start doing crazy things at random intervals. It just seemed to start running instructions which were absolutely not part of the of the program. Like it was running instructions that it shouldn't have gotten from the ROM. So I eventually found out through some experimentation that the whole setup here was so unstable, it would start crashing if the oscillator with the crystal was just running, but not even connected to the chip. Basically, this oscillator seemed to be more stable, but if I had the original clock circuit run, basically what I did at first is I had the original clock circuit running here with the crystal oscillator, and then I had this over here, and it was running the CPU from this circuit here. So the original clock circuit was here, but not connected to anything. It was totally disconnected from the CPU. And I noticed that just having it running there would cause the CPU to crash. So what I ended up doing is I pulled everything off. I pulled the 7404 chip off. I pulled off the crystal oscillator and everything associated with the clock circuit there, and then it was rock solid. Then it just ran perfectly and would just keep running and running and running, and I couldn't I couldn't observe any problems with it after that. So the original clock circuit was causing the CPU to crash just by virtue of being on the board, not even connected to the CPU. So I think I have two theories as to why that was happening. The first possibility is that it was somehow generating some electromagnetic noise. Basically, the oscillation was so noisy that even though it wasn't connected to the CPU, it was creating enough digital noise in the wires that it was screwing up the signals somewhere there. But I think also I might have had a power problem, because I was checking the voltages on my power supply, and I noticed that sometimes, when I changed things on the board here, the supply voltage would sag a bit. I'm running this on 5 volts. I'm running this off a 5-volt DC power supply. But when checking it with a voltmeter, I would notice that the voltage would sag noticeably when changing things here on the board. When I was trying to diagnose things, just pulling wires here and there, I would actually see the supply voltage drop, not by a huge amount, but by maybe something like 0.2 volts, which is a fair amount for something like this. When you're running on 5 volts, 0.2 volts is a lot. These chips are actually extremely sensitive to voltage fluctuations. If you have 5 volts and you lose, less than 5% of that, you might think that's not that much, but it can actually really be a lot for these chips. I believe this 6502, this chip here, is rated for a maximum of 5% power deviation. That means if you're running it on 5 volts, you can go down as low as 4.75 volts before it's out of spec, and then it may crash or something like that. So I suspect, my suspicion, I don't know this for a fact, but my suspicion for the problems I was having was I had problems with the power supply. The power supply just wasn't having it. It's partly my fault for getting a really cheap power supply. So the power supply that I'm using is this thing here. It's just a simple little wall wart, and it's not even fixed. It's actually, if you look at it, you can see there's a little little thing on it to choose the voltage. So you can choose 3 volts, 4.5 volts, 5 volts, 6 volts, 7.5 volts, 9 volts, or 12 volts, and I'm wondering if I might have actually damaged this power supply a bit, because when I first got it, it really would, when I had it set to 5 volts, it really would output 5 volts, like right on the dot. If you checked it with a voltmeter, it would show exactly 5 volts. But now when I turn this thing on, when I plug this in, the output is only around 4.9 volts. That's not good. So I'm wondering if somehow I might have actually damaged this a little bit with something, and I don't know how I might have done that. I don't think that I created any shorts, but maybe I did. It's possible also that the frequency had something to do with it because this is. I'm pretty sure this is a switch. Yeah, it says right on. It's a switching power supply. It's not a linear power supply, and high frequency oscillation harmonics are known to cause problems with switching power supplies. I remember hearing some years ago that's one reason why you don't want to run a VFD, a variable frequency drive. You don't want to run that on the same power line as, for example, a computer, because you'll probably destroy the computer. The computer has a switching power supply inside it, and you can have a situation where, if you have like an electrical outlet with two power outlets on it, you can plug the computer in here, you can plug the VFD in here, and have no other connection between them other than that they're just plugged into the same power outlet, same power socket, or the same power strip or whatever, and the VFD will destroy the computer because it creates such weird frequencies that go through the power lines, and it actually destroys the switching power supply inside the PC. So it's partly my fault for using a really cheap power supply like this. I don't think that it's a problem with the current being too high because this power supply is rated for 1 amp, and I find it extremely unlikely that all this stuff together was drawing more than 1 amp of current. I find that extraordinarily unlikely because all of this stuff here is rated well into the milliamp range. Like there's no way that all this stuff together was adding up to 1 amp of current, but yeah, just somehow the power supply didn't like it. So either there was a short somewhere or something with the frequency, or maybe that chip was just drawing an insane amount of current when it was oscillating, which is plausible, but I consider it unlikely. If you're doing something like this, it's probably a good idea to get a big, beefy linear power supply. When I first built this project about 20 years ago, I had, a big brick of a power supply. It wasn't just a little. I mean, this is made for portability. It's made to be small and portable and, convenient, which is fine for many applications. But for something like this where you really need rock solid power, I mean, I don't know if this is even regulated. Is this even a regulated power supply? It doesn't say that it is, so it might even be an unregulated power supply, which means it's actually pretty bad to use something like that for this. So when I did this the first time, I had a huge power supply, and that thing was dead reliable. You could draw a lot of current from it. I mean, obviously it wouldn't deliver hundreds of amps, but it could deliver a fair amount of current with no sag in the voltage supply whatsoever. It wouldn't the voltage wouldn't sag. It wouldn't. It was clean, like there wasn't any ripple or anything on the DC power supply, and it wasn't being a linear power supply. It also wasn't sensitive to high frequency noise on the power lines. So that's really something good for a project like this. And obviously, a regulated power supply is important. I think I'm actually doing this with an unregulated power supply, which is pretty bad to do. It's actually a really bad idea. But I was trying to do this cheaply because, again, I'm not going to do anything with this when I'm done. So I didn't want to spend a huge amount of money on a really nice power supply just for something that I'm only going to run once and then be done with. So my assumption at this point is that I had a problem with the power supply. It didn't like that clock circuit that I had, but it seems to run fine with this clock circuit. Like I said, it's running at 4.9 volts, which is not good, but it'll work. It's within tolerance for these chips, so it seems to be working. As long as it works for this video, that's enough for me. I mean, really, like I said, if you want to do a project like this, you probably shouldn't use something like this. I've particularly had bad luck with these adjustable power supplies. Like I had one before where if I set it to 5 volts, I think I got like almost 7 volts. I got like 6.8 volts out of it or something like that. And that supply was factory new. This one at least gave me the correct voltage when I first bought it, and then it went down when I used it. So I think I might have damaged it somehow. But that other one was just wrong right from the store. Store new, and it was already giving me completely wrong voltages. So I've had bad luck with these adjustable voltage power supplies. I think you might have better luck by getting one that's fixed, but they're hard to find. I mean, that's the thing. You know, stuff like this, it's not really a consumer item. It's really something more for hobbyists. So you'd have a hard time finding a really good power supply at a local store almost anywhere in the world today. So I mean, again, if you're going to do something like this, I recommend getting a really good power supply and not something cheap like this. I mean, I think this cost me only $10, which is really cheap for a power supply, actually. So yeah, so basically my big mistakes were I'm using a bad power supply. I'm using a really dinky power supply, and I guess, oh yeah, that's right. The other thing, the other mistake that I made was mixing TTL and CMOS. So this is a CMOS CPU. This is a CMOS version of 6502. This ROM chip, this EP ROM chip, is also a CMOS chip. What I did in the last video is I had two TTL chips controlling them. So the chip that I had up here was a 74F04, which is a fast TTL chip, but it's still a TTL chip. And this down here, I had a 74LS138, low power Schottky, which is also a TTL technology. So what I've done is I got a CMOS version of this chip. So this here now is a 74AC138. So basically, if you want to get CMOS chips, you can get, for example, HC, which is high-speed CMOS. You can get AC, which is even faster, and AC stands for advanced high-speed CMOS. There's also FC, fast CMOS, which is probably better, but they're hard to find. So AC is fine. This is like I said, the 74AC138 should be fine. I did also try using a 74AC04 here instead of the 74F04. It didn't help. I was still having the same problem, so that wasn't the problem. But mixing CMOS and TTL in general is not, it can work, but it's not recommended, especially for high-speed stuff. It probably doesn't matter now because I'm running this at a fairly low frequency. I'm running this at, like a few hertz, maybe a few dozen hertz. So I don't think it matters. But that kind of thing can also lead to serious timing problems because CMOS and TTL might have different ideas about how fast that voltage needs to rise or fall. And so you can end up with really serious timing problems if you mix CMOS and TTL. So try to avoid doing that. So that's a classic error which I made, but anyway, so the long and the short of it is, what's changed since the previous video, since the end of the previous video? I changed this chip. So before I had an LS, a low-power Schottky version of this chip. I replaced it with an AC, advanced high-speed CMOS version of this chip. And then the clock circuit here is completely changed. Instead of that clock circuit that I showed in the first video, I have this clock circuit here, which is very simple, but it works fine. It runs fast enough. I mean, the program that I'm going to run here is a few bytes long. It's not even 100 bytes. It's less than 100 bytes, so it's really simple. The whole program will run in a second or two, even at this low speed that we're running at here. So I changed this chip, I changed the clock circuit, and everything else here should be the same as at the end of the previous video. The wiring may look a little bit different in some spots because I moved around a lot of the wires while trying different things, but other than that, this should be fundamentally the same thing that we had at the end of the previous video. So that was that. I spent a lot of time trying to diagnose this and figure out what was wrong with it. And again, it's really hard because I had just two things. It's easy if you can just eliminate one thing at a time, but I was in a situation where basically I had the CPU, I had the ROM, and they worked individually, but they wouldn't talk to each other. They wouldn't work together. At that point, there's nothing more that you can eliminate. You have two things. They work individually, but they don't work together. There's nothing more that you can eliminate from that equation. So there wasn't anything I could simplify. So I was really, the reason why this video came a few weeks after the previous one is because I've been literally spending weeks. I've been trying to go at this for weeks, trying to figure out what was wrong with it, and it looks like it's finally working. So again, the solution was basically get a different clock circuit, get a nice slow clock circuit which doesn't consume too much power. It seems to be working now. Again, that's a luxury which you wouldn't have with the original 6502, but that's something we can do here. So, okay, I'm going to go ahead and pause the video just for a second because I've already been talking for over half an hour. So just so I don't go onto a separate video file with this portion, I'm going to pause the video just for a second. Okay, here we go. And now we can continue. So, yeah, so that's that. So this should be running, this computer should be running as it is. And what I'm going to go ahead and do is, I guess I'll just start talking about the I/O chip. Ideally, it would be nice if I could show how to diagnose the CPU and the ROM talking to each other. But really, the only way to do that is to probe the address bus pins and the data bus pins. You can do that. You can actually put LEDs or, oscilloscope probes or voltmeter probes or something on the chip pins to see that they're doing the right thing. But I'm not going to show that here for two reasons. First of all, the wires here are so dense that you couldn't really see very well what I was doing. I mean, I guess I could turn it around. You can kind of see a little bit better, but you wouldn't be able to see very well because the wires here are already so thick together. And secondly, and perhaps more fundamentally, diagnosing a ROM like this, like the CPU ROM interface, is really dependent on what program you have loaded. I have a specific program here in that ROM chip, which I wrote myself. It's a very short program, just kind of like a test program. And I know what it should look like on the address and data bus pins, but your program might be completely different unless you use my program. But even so, it's totally program dependent. So I'm not really going to show how to diagnose that, but I did check it, and it looks like it is working now. So it's kind of unfortunate. I just want to mention in passing one problem which you might have. I thought that, building this circuit, I thought that one of the hardest things would be to find a 6502, but that part wasn't that difficult because, again, the WDC still manufactures this chip. You can actually still buy it online for $5. What was actually a lot harder, surprising to me, was getting a parallel EEPROM chip. The thing is, parallel memory chips are kind of dying out. They're becoming a thing of the past because it's easier and cheaper and faster to build a serial memory chip, which means instead of having one wire or one pin for every bit in the memory, it's just all strung together on one wire. You've just basically got one wire that carries the entire string of bits. It's cheaper because obviously the chip is physically smaller because it has less pins. And you might not think that's a big deal. I mean, you might think, okay, well, the chip is just a little bit of plastic and metal, so surely the size of the chip can't make that big a difference. It actually really does make a difference. It used to be when chips like this first became a thing, the silicon inside was what really cost a lot to build, and the actual, plastic, just a few, just a block of plastic and a few metal pins in it, that was super cheap by comparison. Today, it's the opposite. Today, electronics manufacturing processes are so refined, and they manufacture these things in such huge volumes that manufacturing the actual little wafer of silicon that's inside there is incredibly cheap. That costs pennies. And the actual cost of the plastic and metal housing is not insignificant. I mean, obviously it doesn't cost hundreds of dollars, but it may cost, for the cost of the plastic and the metal, it may cost $1 or $2. And you might think, okay, well, saving $1 or $2 isn't that big a deal, but if you manufacture 1 million of these chips and you save $1 on each of them, guess what? You've just saved $1 million. So electronics companies will obviously do that because they manufacture in such huge volumes. So yeah, today the actual, just plastic and metal that's in the housing of the chip is a not insignificant part of the overall chip's manufacturing cost. And so manufacturers do want to try to eliminate that where they can. And the thing is, parallel memory chips like that, they don't have much application because nobody's using them. They have no application in the professional market because professionals use serial memory chips because they're faster anyway. And hobbyists, how many hobbyists actually build something like this? Even most hobbyists aren't building something based on a 40-year-old CPU. They're building things, if they're building something like this, they're probably using an Arduino or something like that, where you don't need a parallel memory chip anyway. So it's kind of a It's kind of unfortunate. The parallel ROM chips like this are actually becoming a thing of the past. They're actually becoming really hard to find. This chip is made by Atmel, and I tried so hard to find a different memory chip, a different parallel EEPROM chip that I could actually, readily buy. And all the ones that I could find are also made by Atmel, which, I have nothing against Atmel, but I wanted to try a different manufacturer and I couldn't find one. And I don't know how long those Atmel chips are going to be available, because I think a few years ago Atmel was bought by Microchip, by a company called Microchip, and all the chips that I could find still have the Atmel branding on them. So I think those products are also going to be a thing of the past. They're probably not going to be sold very much longer in the future. So yeah, it's kind of unfortunate. Ben Eater, in his videos on the 6502, he used an Arduino basically as a ROM in his project. Which you can do. I mean, the Arduino has ROM built. It has memory built into it. You can use it in that sense, but it's kind of like it just seems a little bit ridiculous. It's kind of like you're using something which is much more powerful than this CPU. I mean, the Arduino is way more powerful than the 6502. You're using something that's much more powerful to get something that's less powerful to work. I mean, if you want to do something like that, if you want to get an Arduino to make this work, you might as well just use the Arduino. The point of this is to show how all this stuff works. So yeah, kind of unfortunate. But anyway, okay. Let's go ahead and talk about the I/O chip. That was actually supposed to be the main focus of this video. So now after like 40 minutes of talking, now I can finally talk about what I meant to talk about in this video. So this guy here, this is also made by the WDC. This is the 65C22. It is a... I think the name, like the marketing name for it, is the VIA, the Versatile Interface Adapter, but it's basically an I/O chip. So basically it facilitates communication between this computer and the outside world. This is now a running computer in the sense that if you turn it on, it will run. The CPU will get instructions from the memory and it will run those instructions, but that's not very useful because it can't connect to anything. So for a computer to be useful, you have to connect it to something. Usually a computer has an input device like a mouse or a keyboard, and it usually has an output device like a monitor or something like that. So most I/O, though, goes through a chip. You can't just write directly to an I/O device like you can write to memory. So, a CPU can write to a memory address, but most devices that you're familiar with won't have a direct, memory address. There is memory mapped I/O. In fact, this computer is going to use memory mapped I/O, but the device that has an I/O address is not a direct I/O device. It's actually this I/O chip. And that's true in PCs today as well. I mean, if you think about most devices that you can connect to a computer, most I/O works through some kind of controller chip. I mean, disk drives, like hard drives or CD-ROM drives or so, they will have a drive controller. They don't just connect directly to the memory. USB devices will have a USB controller chip. So like inside your PC, there's a USB controller which handles connections to USB devices. So USB devices also don't connect directly to the CPU. Even going back to serial ports, RS-232. RS-232 devices had a UART, a Universal Asynchronous Receiver and Transmitter, and that was what basically enabled the RS-232 interface. So that also, RS-232 devices wouldn't connect directly to the CPU either. So most things have an I/O chip which kind of drives them. So what I'm going to do, this guy here, excuse me, this is the WDC's diagram of the chip. It's a little blurry. I actually printed this directly from their datasheet. I don't know why it's so blurry. It looks blurry in their datasheet as well, but it's readable. So, yeah, VDD and VSS are the voltages, just like on this. This chip also has, so VDD is the positive power source and VSS is the negative power source. the letters stand for drain and source. So this is the source because this is where electrons come in. So, electrons are negative, and so this is the negative side, and this is the source because electrons come into the chip through here, and then they drain out this way. So electrons are drawn to the positive side, and so they drain out the positive side. So that's how you know that this VDD is positive and VSS is negative. Electron source, electron drain. This chip is the same. So yeah, so we'll hook up those two power pins. Over here on the right, there is a data bus which will connect directly to the CPU's data bus. So we can just, this chip was originally made by the same company that made the 6502. It's part of the same series. That's why, the numbering is similar. And they're designed to work together. So a lot of the pins are designed to be just directly connected. So like, for example, this Phi 2 pin, which is kind of like an enable pin, that connects directly to the Phi 2 output of the CPU. And these data bus pins connect directly to the CPU. And where's the, the read-write pin here connects directly to the CPU's read-write output as well. So these chips are made to work together, and so again, it's really just like connect the dots. It should be fairly simple. These pins on the left, all these PA and PB pins, these are the actual I/O buses of the pin. So it has two I/O buses. Each has 8 pins. So connector A, if you will, has PA0 through PA7, and then connector B has PB through PB7. So you basically have 2 I/O ports with 8 pins each, 8 wires each, and each pin of these can be both an input and an output. These CB and CA lines, we're not going to use that for this project. In fact, I'm going to go ahead and cross those out. Those are used for like communications protocols and things like that, which is pretty cool, but for this simple project here, we're not going to use those, so I'm just going to cross those out right now. Also, this IRQ line, this is not an input, this is an output. So you can use this to send an IRQ signal to the CPU. We're not going to use that either. We are not going to use interrupts in this project, so I will go ahead and scribble that out. So what do we have left? We have... So on this side, there's just the power pins and then the 2 I/O buses, PA and PB. Over here we have RWB that goes directly to the CPU's RW. The 2 chip select pins to turn the chip on. We're going to use this decoder chip for that. So basically, this I/O chip will have its own memory range. And so just as we gave the ROM chip a memory range by putting it on this pin here, we're going to give this chip a range by putting it on a different pin of the memory decoder. So that will activate this I/O chip when the CPU is reading a specific memory range. So yeah, so we'll trigger these through the, well, one of these will probably stay on and one of these will be triggered by that memory decoder chip. The Phi 2 input, that is going to connect directly to the CPU's Phi 2 output. The data bus will connect directly to the CPU. This is the reset signal, which we will connect exactly as we connected the CPU's reset pin. These RS pins, that's register select. So this I/O chip has internally, it has a few different registers, and those RS pins allow you to select what register you're accessing. And then these CA pins, which we're not going to use. So that's it. So you know what I'm going to do? Before I connect this to the CPU, actually, I'm going to stick it down here, and I'm going to show you how to kind of operate it by hand, which is kind of cool, maybe. So there we go. So now it's in the board, and I do have my wrist strap on, and so I am good to handle stuff like this with my hands. So what are we going to do here? I will go ahead and I actually wrote out a very simple little test that we can use. So let's look up the power first. So, whoops. I bumped my camera a little bit, but that's okay, it didn't fall off. So, so pin 1 up here is VSS. Remember, that's the electron source, so that's negative. And then pin 20 down here is the electron drain, so that's positive. So I'm going to go ahead and connect pin 20 here to the positive voltage rail. And I'm going to connect pin 1 to the negative voltage rail. There we go. Okay, and then these pins here will be our outputs, but we'll worry about that later. And what do we need on the right-hand side? I'm going to go ahead and actually, I'm not going to read anything from this. So this, like I said, these I/O pins here, they can be both inputs and outputs, but I'm just going to write to them. For this quick test, I'm just going to use them as outputs. So write will always be in write mode. I'm not going to read anything. I'm always going to write. This pin is write low, which means when this pin is low, you are writing to the chip. So I'm just going to tie this to low voltage. I am going to tie this to, tie pin 22 to ground, and then it will always be low. It will always want to be reading things. The two chip select pins, I believe, let me see. Yeah, so the WDC, for whatever reason, uses B to indicate an active low signal. So that means that this signal is active when it's at a high voltage, and this signal is active when it's at a low voltage. So I will tie pin 23 to ground and pin 24 to the positive voltage, so that the chip stays on. So pin 23 can go to the 0 volt side of the power rail, and pin 24, pin 24 can stay high. Okay, what else do we have here? Oops. Okay, there we go. Now it almost fell over. I need to be careful, man. I need to stop knocking stuff around here. Okay, so where was I? Right, so we need, like I said, we need a reset signal on pin 34. It works exactly the same as the CPU's reset signal. It's active low. So what I'm going to go ahead and do is take a 3 kilo ohm resistor, like this one here, and I'm going to put it on pin 34. That is 1, 2, 3, 4, 5, 6, 7. That's the 7th pin from the top here. So 1, 2, 3, 4, 5, 6, 7. I'm going to put that in there, and I'll put the other end on the positive voltage. That's right, isn't it? 1, 2, 3, 4, 5, 6, 7. Yeah, it looks right to me. Okay, and then what I'll do is I will take a little button, like this one. Here's another little button, and put it somewhere. I mean, I'll just put it anywhere, I guess. I'll put it here, why not? And so one side of this button I will connect to that reset pin, and the other side of that button I will connect to ground. So now when I push the button, that reset pin will be shorted to ground, and when I release the button, it will get pulled up to positive 5 volts through that pull-up resistor. Okay, good. Reset button is taken care of. So now we need to go ahead and, right, okay, I need to wire up some of these pins here. We're going to want to send in some data into the chip through this here, and we're going to want to choose an internal register of the chip through these pins here. So let me go ahead and pause the video just for a bit. I'm going to go ahead and start wiring some stuff up. Hey everyone. Okay, so I've gone ahead and put a few extra wires on the I/O chip, and now I think I'm ready to demonstrate it. Let me actually see, let me see if I can get the camera to focus just on that part a little better, because you don't really need to see the whole board now. I really just want to look at this part. So maybe I can, does that help a little bit? Maybe that helps just a little bit. We'll see. Okay, so here's what we can do now. Let me go ahead and briefly explain. So again, these are the outputs here. So I've got 4 LEDs here that'll show what are coming out of the first 4 pins of PA. So PA is output, well, input and output register A. So I'm going to go ahead and try outputting something on the first 4 pins of register A. The yellow wires here set the register select, so this will select a particular register in the I/O chip. These 4 orange wires, that's the first 4 bits of the data bus, so that will control the actual data that gets sent into that register. And then this green wire is the enable pin, so I will use this to actually make something happen after I've set up the wires the way I want them. So let me go ahead and apply power to the board. And you can see the LEDs have turned on. It might be a little bit, yeah, maybe a little bit easier to see if I shadow them with my hand a bit. You can see the LEDs are on. I think that's the default state of the chip, that they're just, actually, I don't know what the default is. Are they on, or I guess they are. I mean, they're definitely emitting light, but I'm not sure if they are actually technically on, or if the pins are acting as an input and the inputs are letting some current through, and that's why the LEDs are on. I think both are possible, but I don't know. Anyway, it doesn't matter. So the first thing we want to do is set these 4 pins to be outputs. Make sure that they are definitely outputs. So for that, since this is register A, I will use, I will set register number 0011. That is data direction register A. That's the data direction register for I/O bus A. So we have the 4 register select pins here. So again, the register number is 0011, and it starts from here. It actually starts from RS3. So that needs to be 0, that needs to be 0, that needs to be 1, and that needs to be 1. So we have the wires here. So let's see. So that goes to ground. So that will be 0. This one also goes to ground. That will be 0. But these other 2 need to be 1. I will put them on plus 5 volts. Okay, now what data do we want to send? If we send a 1 into a particular bit, then the pin for that bit will be an output. Otherwise, it will be an input. I want these to be all outputs. I just want to send stuff to the LEDs. I don't want to read anything in through these ports. I just want to send to the port. So I will make sure that all the data bits are 1s. They all are. They are all on plus 5 volts. So I will go ahead and toggle the enable line, and you can see the LEDs all turned off. As soon as I did that, they turned off. So the CPU is now out, or not the CPU, the I/O chip is now outputting whatever is in register A. Register A is now an output, and it's outputting whatever is on that. So let's go ahead and do this. Let's create an alternating pattern of 1s and 0s. So let's do 1 0 1 0. So I have the data bus here. So I'm going to go ahead and, so this top one can be, that's correct, isn't it? Yeah, this is D0. So I'm going to go ahead and leave the top one at 1, and I'll make the second one 0. I'll leave the third one at 1, and then make the fourth one 0. So now we have 1 0 1 0. Now I need to select the correct register, and for output port A, that is going to be register 0001. So this one needs to be 0. So now we have 0001. That looks correct. Okay, now is the big moment of truth, everyone. Now let's see if this works. I'm going to shadow the LEDs so you can see them better. And as soon as I pulse this wire, we should have on, off from the LEDs. Is it going to work? I didn't even need to push it to 5 volts. It worked as soon as I lifted it off ground. Awesome. So there we go. On, off. There you go. So first you set the port here to be an output, and then you send the data into the output register for that port. In this case, it's at 1010, and boom, there you go. Right away, we have an output of 1010. And if I press the reset button, it resets and all the LEDs come back on. Awesome. I'm going to go ahead and unplug this. And there you go. So, how are we going to interface this to the CPU? Well, what I'm going to do is, so obviously we connect the power pins. I'm not going to worry about these actual I/O lines yet. I'll leave that for later. Like I said, this goes directly to the CPU's read-write pin. This will be activated by that memory decoder chip. CS1 will stay on. Phi 2 will go to the CPU's Phi 2 output. All these 8 data bus pins will go directly to the CPU's output. The reset pin will be configured just like this with a button and a pull-up resistor. And then these reset lines, these four, sorry, not reset lines, register select, these four RS, these four register select lines, these will go to the CPU's address bus. So what's going to happen is RS0 will connect to the CPU's A0, address bus 0. This will go to A1, this goes to A2, and this goes to A3. What's going to happen then is when the CPU checks for a specific memory address, it is actually accessing specific registers inside the I/O chip. So that's what's called memory mapped I/O. Technically this is memory mapped I/O because the CPU is writing to what it thinks is a memory address, but what's actually happening in reality is it's not being written to a memory chip like that ROM chip there, it's being written to this I/O chip, and that can be reflected in real world things like, for example, these LEDs. So I'm going to go ahead and pause the video for a while. I'm going to move this chip. You know what I'm going to do? I'm going to actually flip this chip around. I'm going to flip it upside down from where it is now. The reason for that is because the data bus and all this other stuff that needs to connect to the CPU is on this side of the chip, but I have the CPU over here. So if I put the chip here, I would have to jump the wires from here over the chip to here, which is doable, but a little bit silly, actually. Just thinking, yeah, because what I'm going to do is so this chip needs to connect with this chip, and then the outputs, which are going to be, over here, it would be silly to have the outputs here and the side that need to connect to the CPU here. So what I'll probably do, I can't get that out that easily. Let me pry it out. Ideally, I'd have a proper chip puller, but I don't, so I'm just going to carefully pry this up using these tweezers. Come on. Come on. I'm going to very carefully extract it. Okay, is it going to come out now? Come on, you. Wow, that is stubborn. That is one stubborn chip. It does not want to come out. Okay, a little more coercion, a little more pulling, or pushing, or some combination of both. Come on, I see you coming out there. There we go. Okay. So yeah, so what I'm going to do is I'm going to turn it around so it's upside down like that, because that will mean that the parts that need to connect to the CPU are on this side, and then my outputs will be here. That makes a bit more sense. I think the only problem with that, the only thing that's a bit annoying about that is, yeah, if you look at the CPU wiring diagram and compare it to this thing's wiring diagram, the nice thing about having them oriented the same way would be I could just run these wires directly to each other. So D0 would go to D0, D1 would go to D1. If I have this upside down like this, the wires are going to cross over. So D0 will have to cross over to D0 at the bottom, will have to cross over to D0 at the top on the other side, and D7 at the bottom of the CPU will have to cross over to D7 at the top of the I/O chip. So I'm going to have 8 wires that are kind of like cross-linked against each other. It's doable, it's just going to look horrible. It's going to look really ugly, and it's going to be kind of awkward to wire. It would be a lot easier to wire it straight through, but the benefit then is I have my outputs here, so I can just connect my, connect LEDs or whatever directly on this side without having to kind of try to fit them in here, which could get awkward. So, okay, so I'm going to do some wiring here, and I'll restart the video when that wiring is done. Okay, so it looks like this. I've zoomed in on it a bit. That green wire, so this green wire coming down here, this is what enables the I/O chip. So this is coming from the memory decoder, and that will enable the I/O chip when when the CPU is accessing a certain memory range. This is the reset button for the I/O chip, and this is the reset button as ever for the CPU. So the way that you operate this computer is very simple. You press both buttons, you release the reset button for the I/O chip, and then you release the button for the CPU. And then the CPU will start talking to the I/O chip and sending it instructions. So it should have worked. You can't see anything though because we have no output. We have no visible output here. So I'm sorry that this looks terrible, but that should work. This is basically all the connections that I talked about. So I connected, what did I connect? Again, I connected the 4 RS lines to the register select lines. The reset button obviously is here active. The 8 data bus pins, the Phi2 enable pin. These 2 pins are hooked up. This is tied to 5 volts, and this is tied to the memory decoder there. This is tied to the CPU's read-write, and then I just put the 2 power pins on, and that's it. So we have our outputs here. So I'm going to go ahead and actually, what I can quickly do, just to check that very quickly, is stick an LED here, and then it works better if the LED actually goes in. There we go. That should be good enough. And I'll take a resistor. You always want to use resistors with your LEDs because otherwise they will burn out if they do not have any kind of current limiting in place. Okay, and I will take a wire like so and start probing the different pins on the chip. And actually, you can't. Okay, change of plans. Let me move this down a bit because you can't actually see all that very well if my hand is covering it, can you? So let me try again. Let me put this down here then, so that my hand will not obscure it. Put the wire there, like so. And so now when I touch this to positive 5 volts, yep, the LED comes on. Okay, so I'm going to probe these pins, the output pins, on the I/O chip here. Hold on, did I run? Let me just run it one more time. So reset both, release that, release that. Okay, let's try probing the pins here. Okay, good start. So that's off, that's on, that's off, that's on, off, on. Nice. Okay, so you know what I'm going to do? I'm going to pause the video again, and I'm going to hook up some LEDs here so we can actually see kind of a row of them, kind of see what it looks like. So I'm going to pause the video just for a sec. Okay, and here we are. So I didn't hook up LEDs to all the outputs. There are actually 16 possible outputs here, but I got lazy and hooked up only 8 of them. But we have 4 LEDs on the first 4 pins of the A bus, and then 4 LEDs on the first 4 pins of the B bus. So this should be enough for us to get an idea of what's going on. So yeah, just got the wires going across here, some resistors and some LEDs. Let's go ahead and turn on the power. And, oh, it's actually already in the desired configuration. You can see they're already on, off, on, off. The I/O chip seems to be fairly persistent. It actually stores, or it seems to remember its last state even when the power goes out. But let's go ahead and do a reset. So I reset it, so now all the LEDs are on, and I'm going to hold on the other reset pin, release the reset, or reset button, release the reset button for the I/O chip, and release the reset button for the CPU. And there we go. One nice thing about running the clock slower, this is actually a nice side benefit of having the clock running more slowly like this, is you can actually see things happening. If I was still running this using that 1 megahertz clock circuit that we had before, the LEDs would just almost right away, like you couldn't perceive the time delay between when you released the reset button and when the LEDs actually got into this configuration. But because we're using a much slower clock here, you can actually kind of see what's happening. Let me go ahead and let me first just quickly show you what the whole thing looks like. So there you can kind of see the I/O chip and how I wired that up, and here you see the LEDs. And if I go ahead and turn this sideways, and let's see, let me go ahead and get the power hooked up here. And I'm actually going to turn off the light just for a sec, just so you can, oh wow, that's darker than I thought. Well, I guess I don't really have much illumination here. I just have my laptop Okay, but I think by the light of the laptop screen, I can kind of see. Let's see, where are the buttons? I just need to find the buttons. There we go. So there are the buttons. So I'm going to push the reset buttons. There we go. And now it's resetting. And now I'm going to I'm going to release the reset button for the I/O chip. Now release the reset button for the CPU. There you go. And you can see it's actually quite nice. You can kind of see, like, it doesn't instantly snap into place. It sort of takes a moment to line up the LEDs. If I do it again, it's actually a pretty cool effect. I like that. And you could see it even more if it would happen slower, of course, if I used a slower clock circuit. But I think this is fine. That gives you an idea of what's going on. So, and yeah, these LEDs don't flash. I mean, if we wanted, we could actually. It's kind of interesting. I'm noticing the two here on the left seem a little bit dimmer than the ones on the right. I don't know why that is. It's interesting. It's not a huge difference, but it's definitely noticeable. I think you can see it on the camera, and I definitely notice it in real life as well. Interesting. Anyway, okay. So, some of you might ask, why didn't I make them blink? I mean, what I could have done is have them alternate between 0101 and 1010. The reason is just because that would have been more code. Again, I hand programmed the program that's in that ROM chip there, and that would have just been more work. And I wasn't really interested in, I mean, it's not difficult per se to program the ROM chip. It's just tedious and painstaking, and I didn't want to have to do that more than I had to. So, it's just software. And again, really, the point of these videos is not the software; it's more about the hardware. So yeah, that's really it. And I mean, in terms of timing, I don't really have a good way to time this. I mean, what I have to do is base this on CPU cycles. I'm just thinking, in a real PC, in an actual, like, IBM PC compatible, so to speak, you have an RTC, you have a real time clock, and you can use that to time things. But back in the very early days of microcomputers, when computers didn't always have a proper, a real-time clock built in, the only timing element was the CPU cycles themselves. And so you'd have to time things based on how many CPU cycles had passed between a certain set of instructions, which you can do, and that works fine as long as the CPU cycles, or as long as the CPU speed remains constant. I mean, it works on, for example, something like a Commodore 64, because basically every Commodore 64 in the world is built the same. It has the same components inside, and all the components run at the same speed. But a PC is different. Early PCs ran at a few megahertz, and again, PCs today run at a couple of gigahertz. So again, it's literally about 1,000 times too fast. So there are some programs which, there are some PC programs which do things correctly, so to speak, by basing their speed on the time of on actual timers, like actual time-based timers, which is why some games, like, for example, Alley Cat is a good example. Alley Cat is a great game. It's a great example of a game that still runs at a proper speed, even on computers today. But a lot of early PC games just ran too fast because they were based on the CPU cycles, and then when the CPU ran faster, so did the game. Anyway, sorry, got a bit sidetracked there, but the point is, yeah, I would just have to write, a longer program loop that basically counts out a certain number of CPU cycles and then alternates the LEDs after a certain number of cycles has passed. I could certainly do that. It's just, it's more software writing. I didn't feel like writing a lot of software for this project. I wanted to minimize the software focus. And secondly, it would have been more work than to get all those bits into that ROM chip. So this is it. This is now a running, working computer. It has a CPU, it has memory, and it has an I/O interface, and through the I/O interface you can actually see things happening. It doesn't have any input. Obviously it doesn't have an input device like a keyboard or a mouse or anything like that, but it is, in a sense, a real working computer. And the nice thing about this, I think, more than I mean, some of you might not be impressed by these LEDs, but I think what's more important is it's easy to adapt this computer to certain other applications, because basically this is, at this point, a fully functioning computer. This this VIA chip is actually fairly powerful because it has 16 pins, all of which can be inputs or outputs. And if you want, if you really want to get fancy, you can add a second VIA chip here and just have them both running in parallel at different, just different memory ranges. Then you've got 32 inputs and outputs, which is fairly powerful, actually. You can do a fair amount of stuff with that. So yeah, basically if we wanted to do something else with this computer besides just light up some LEDs, all you need to do is just have whatever hardware device here, hook it up to this I/O chip, and there you go. And then you just need to change the software. So physically, all you need to do is just hook it up to this chip here, and then software-wise, just write software to control it, to talk to whatever devices you had here, and that's it. So this is really is a fully functioning computer. Whatever you want to do with it, you can just add stuff to it. Just add different things to it and write the software for it, and it'll work. So that's it. I guess I'm done. I guess that's really what I wanted to show in this video, and it went on a lot longer than planned because I had the whole problem with the clock circuit doing something weird, and I wanted to explain that. That took up a huge amount of time at the beginning. But I feel like the journey was worth it because we actually have, again, we have an actual working computer here. It actually does something. You can see what it does, and you can program it to do something else easily. So that's basically it. At this point, I'm pretty much done with this video series. I plan to make one more video showing how to use a little graphical LCD. A lot of people, when they make computers like this, they want to use a character-based LCD, which usually has just like 2 lines of text. And it's kind of weird because in most cases, I'm more minimalist than other people. But in this case, it's the opposite. Everybody wants to use a character-based LCD. And I say, no, I don't just want 2 little lines of text. I want to have proper graphics, like real bitmapped graphics. And you can get that with nice, nice, commonly available, inexpensive LCD screens. So I want to make one more video to show how to do that, but that's, that'll be a future video. So this is enough for today. I'm glad that I finally got this to work. I'm a little bit disappointed that I couldn't get the CPU to work with the original clock circuit. Because that is the clock circuit that I got working when I built a computer like this 20 years ago. So it is a little bit disappointing that didn't work. It is also a bit disappointing that, again, this CPU is not a drop-in replacement for the original 6502 because of those 2 wire changes. First of all, you need to enable the bus enable pin, and pin 1 is actually an output here and not a power input. And also because it's CMOS, you probably don't want to interface it with TTL chips. So this is not just a drop-in replacement for an original 6502, but functionally it works very similarly to 6502, and with some relatively simple modifications, I would say, you can make a 6502-based computer that works kind of like a computer that would have been based on this CPU or a similar CPU in the 1980s. But yeah, I guess that's it. We're done here for now. So thanks for watching, everyone. Feedback and questions are welcome if anybody has any. Otherwise, yeah, have fun and thanks for watching. I will talk to you folks later. Bye-bye for now.